Hello, this is John Kavanagh from D&V Software, and this is a quick guide for the gas network model using Maros. The system that we are going to design is a compressor station, with two stations A and B feeding one gathering system, with station A dealing with 60% of the flow, and station B dealing with 40% of the flow, and the central processing facility dealing with 100%, with each station having two compressors in parallel. There is a huge distance between all of the stations, and there is also one location specifically for the maintenance resource. Once you've opened Maros, a window with three options will open. Choose the Create a New Model option. The first thing you need to do is add information to the simulation parameter window. So set a system life to 10 years, a design capacity of 500 with units of mmscf per day, and then a number of simulations to 100 cycles, and OK this dialog. Save the model by clicking File, Save As, and save the model as Gas Network. We are now going to build the network system that is described above. So open the equipment catalogue using the arrow in the top right and drag the compressor station to the main view. Change its description to station A. OK the dialog, and do the same for station B. And for the CPF. OK this dialog, and click on the gas network study name on the left hand side of the software. Connect the branches using the connection tool. And always connect the branches from the downstream part to the upstream part, so in this case from right to left. You click on the CPF and hold the mouse button and drop it on station A, and then do the same for station B. We must now define the flow. It is known that after the third year the production shows a decline of 5% per annum. So open the flow table by going to View, Flow Table, and in this flow table, the grey column on the left, right click on, and go Insert Series, inserting a series with 10 rows in step units of years and step values of 1, starting from the 1st of the 1st 2012. And we'll now enter the values. We insert a flow loss of 3% per annum after the first 3 years for station A, and a flow loss of 2% per annum for station B, and the software works out the total flow for the CPF. We will now revert back to the assets view by going View, Main. We now need to build a system on each station. So click on station A, add a new system using the SY button in the toolbar, and right click on it and change the properties and the description to Compression A. OK this dialog. Open the input catalogue, use the filter and select compressor, and select the compressor and insert it into Compression A, naming it Compressor A. Right click on compressor A at the asset view and convert to parallel blocks of 2 by 100. Now click on the compressor A at the system level on the left hand side of the software. Copy and paste it into station B. Right click at the parallel block level, go to properties and change the description to compression B and OK the dialog. We must also name the folders and the compressors as B, and we will do exactly the same thing for the CPF, naming each level compression or compressor CPF. We must now define the percentage of flow through each station, with station A dealing with 60% of the flow, and it has two parallel units with each train therefore dealing with 30%. And station B deals with 40%, so each train deals with 20%, and the CPF deals with 100%, so each train deals with 50%. So click on the compression A and right click on the first parallel unit, go to properties and change its percentage to 30%, and do the same for the other parallel unit. And station B, do the same thing, but set it to 20%. And 50% for the compression CPF. We must now define the event. So to do this, click on the gas network study name, then go to View, Equipment Table. In the equipment table, you can scroll along the different parameters. You can also use Field Chooser to minimize the size of the table. So firstly, we need to change the names for each of the equipments to distinguish between each train. So set compressor A1 and A2 and do the same for compressor B and CPF. We then need to set all MTTFs to 0.1. All failure types as exponential, as they are already set as that in the default. And the repair types need to be rectangular, with the minimum time for repair set as 12 hours and the maximum time set as 36 hours for all the flows. Once all these parameters are changed, we must define the resource. At this point of the model, we start to define the resources that we need to repair the possible failure. So go to the Resource View tab, and in this tab there is already a default location. You can change the name of this location to Compression A. OK the dialog. We also want to input 3 more locations for compression B, CPF and the resource location. So use the LO button to insert these new locations and place them appropriately. With compression A and compression B in the same locations as they were in the Asset View main tab, and a resource location in between these two compressions and the CPF to optimize the efficiency. Finally, the CPF, a great distance away from compression A and compression B. We now want to put in some resources at the resource location. So click on the resource location, and we want to input a crew and a spare. So use the CR button and the SP button. Double click on the crew to open the dialog. Change the description to mechanical crew. And in the skill mix tab, add a skill, name it general, and leave the number in the crew as 1. In the optional constraints tab, check the box requires mobilization time, and we need to set the hours between a minimum of 1 and 2 hours. OK that dialog, and then check the box for the constraint by hourly shifts if it isn't already ticked. Click on the blue field and set the start time to 8 o'clock in the morning and the end time to 8 o'clock at night, and OK the dialog. OK this dialog also, and use the crystal ball with a hand symbol, which is the view change simulation parameters, where Maros will assume that there is no shift overrun. So once the shift is over, the equipment is left unrepaired until next morning. You can override this by selecting Keywords tab and ticking the box marks shift, and OK this dialog. To change the input for the spare, double click on the spare. On the General tab, change the description to compressor. And the number in stock to 12. In the replenishment data, change the replenishment level to 4. And the time to restock range from 30 to 30 days. This means that every time that we reach the level of 4 compressors at our resource location, we will order a new set which will take 30 days. So OK this dialog. We now want to assign a location to each branch. So go back to the Assets view. Right click on Station A. Go to Properties. In the location, select Compression A. OK the dialog. Right click on Station B, and in Properties select the location as Compression B, and OK the dialog. And in the CPF, set the location to CPF, and OK the dialog. We now want to assign the resource to the failure modes, so click on the CPF and then go to View, Equipment Table. Scroll along until you find the Maintenance Profile column, and click in Create/Edit and select the crew and spare from the type. Check the option Use Profiles and type CPF at the Create New option. Click Apply and then close the dialog. Maros and Tarot give the user the ability to prioritize the repair of the most critical systems and equipment. There are 3 degrees of priority: emergency, next shift, and next visit. Within these 3 classes of priority, there are 5 different levels. The repair priority is based on production, therefore the priority of repair should be CPF system, station A, then station B. Hence the job priority for the CPF system should be set to level 6. We now need to select the same maintenance profile for the second compressor in the CPF. For station A, create a station A maintenance profile with the same input data as CPF and change the job priority to 7, and now do the same for station B. You create /edit, tick the use profile box, use the CPF, change the job priority to 8 for station B, and in the create new field name it station B, click apply, and then close the dialog and assign the same station for the second one. Now revert back to the asset view by going to the view button and then main. We now want to make the scheduled event, so click on the CPF, add a scheduled event by clicking on SE, double click on the scheduled event and add a scheduled activity by clicking SA. Set the active reference code to ASD, and this code means that the annual shutdown, and set the repair type to constant, and type in 168 in the hours field. When defining the demand profile, we know that there is an annual takeoff of, for the first 6 months of the year, 65% of the design capacity, and for the last 6 months of the year, an offtake of 50% of the design capacity. So to define the demand profile, open the flow table, so go to view, select flow table, and select the option sales, and then right click on the grey column and insert a series containing 20 rows with a step value of 6 and a step unit of months. And OK the dialog, and add the demand information as shown. So for the first 6 months of every year, set the CPF to 65%, and for the second 6 months of every year, set it to 50%. So open the feedstock profile, which is this tab, and you can see that there's a decrease of 5% of the overall production after the 3rd year. Open the sales profile. The black line here represents the demand for a certain period, and for this particular system it shows that there is a lot of spare capacity, which is the extra capacity of production at the beginning of the life of the system, but this quickly runs out, and by 2021 you'll see that there is no spare capacity for the system. We will now run the model. So you run the model using the crystal ball option. when the model runs, you'll see that the performance graph converges to a value, which each cycle representing a possible behavior of the system in terms of production. If a large number of cycles are performed, an average of the life of the system is produced. For this particular model, we are running 100 cycles. Once the calculation has run, the results viewer will open up, and we will now analyse the results. The software provides a large range of results. There's a film strip at the bottom that summarises the most important results in the results viewer. The number of results will depend on the complexity of the model. If you're modelling a flare, the software will provide you results relating to flaring operations. So click on the production summary, where there is a monthly production profile and monthly production volumes figures. And there is also an expert viewer available for the results, where you'll find the results in their raw format. The performance of the system is 94.034%, so it is a pretty reliable system. However, we need to bear in mind that nearly 6% represents a huge loss for an investment of billions of dollars. Let us say, for instance, that gas prices are $3 per 1,000 standard cubic feet. The volume loss over the life of the system is therefore 60 billion cubic feet. This represents $180 million. So if you have access to the values of capital expenditure, operational expenditure, such as the cost of spare parts and man hours, and production pricing, Maros will calculate the NPV for each design possibility. So if we go back to the report viewer, and in the executive summary, you can see that there is a monthly production efficiency and volume figure, and if you click on one of the bars, you can drill down the results to see per month and per day, with the blue areas representing the losses and the green areas representing the production in volume. From the subsystem criticality pie chart, the most critical event is the scheduled element, which is the annual shutdown. And the second most critical event is the CPF. If you click on the event graph, you can drill down events further into the results. And if you pass the mouse over the graph, a row at the top of the graph area will appear. Click on the third icon, which looks like a table, and the results will now appear in a table format. Right click on any of the equipment or events and select View in Maros. This button will take you directly to the equipment that is the problem. We can now show how fast it is to perform a what-if scenario. So what if we slightly change the process and allow the system to use line packing? The ability of a natural gas pipeline to effectively store small quantities of gas in a short-term basis by increasing the operating pressure of the pipe. So most pipelines use line pack as a resource to help manage the load fluctuations on their system, building up line pack during periods of decreased demand and drawing it down during periods of increased demand. The line pack can also be used to recover losses when failure occurs, which is an industry-specified operation which cannot be modelled by entry-level tools. So to model a line pack, go to Production, Security of Supply, and in the Gas Bank Data tab, add Bank. Now let us assume that after implementing the new line pack, we would cover the losses for half a day. So set the volume to 250 and leave the maximum rate at 500, which is the maximum volume that can flow through the gas bank in a single day. And go to the Branches tab and select the CPF branch location and OK the dialog. We now need to define which branch has the line packing. So go to the Branches tab and select CPF, and we now need to allow the system to boost. So on the top right hand side of the software you will find 3 buttons named No Boost, Recovery Boost and User Defined Boost, where No Boost is the default setting for new models and the Recovery Boost is used in conjunction with a sales profile. Normally the production requirement defined by the sales profile is less than the production volume the system is capable of, defined in the normal profile. During normal conditions, the system produces at a rate defined by the sales profile. If an event occurs in one part of the system which prevents the sales profile requirements being met, the system will boost to recover. And the third boosting option is the user-defined boost, which is selected by pressing the third button. If user-defined boost is selected, then an additional data grid tab called Max will be available. So we want to select the recovery boost and run the model. When the results viewer opens, you will see that the performance now equals 95.8%, up from 94%, which is around a 2% increase. So you need to assess whether this change is worth the investment. So let's say, for instance, again, that the gas price is $3 per 1,000 standard cubic feet. The volume loss over the life of the system is 30 billion cubic feet, which represents $90 million, a reduction of $60 million, which informs that about the cost. You can make a decision based on the actual revenue from the system. We can now ascertain which systems are giving more losses, such as we could hire more personnel in order to reduce the time taken by the annual planned shutdown. We could check what is the best day to run the annual shutdown. Perhaps we are running it on high demand season, which could lead to more losses. Or we could increase the reliability of the CPF station by buying more reliable compressors, or by adding a spare compressor. And this exercise can be done until the new implementations are no longer worth the investment. This has been a quick introduction to the gas network model in Maros, showing you how to set up your model and then analyze the results.